Okay, so looking at the wave nature of light again, what we're looking at now is reflection, refraction, and diffraction. So the first two, reflection and refraction, are what we are looking at for the moment. Okay, so basically what you've got is you've got two different media. You've got air is the media colored in yellow here, and the other medium is water, and this has got a higher refractive index. Um, okay, so what you've got is you've got an incident ray, okay, which is propagating towards the more densely optical medium in the water. And what happens is that you've got an angle of incidence. Okay, now the angle of incidence is the angle between the incident ray and this perpendicular to the surface of the media boundary. So this is a perpendicular line here, and it's called the normal to the surface. And the angle between the normal and the incident ray is called the angle of incidence. Between the normal and the reflected ray is called the angle of reflection, and these two should be the same. And if we look to the right over here, we've got black and blue, and yes, 46.7 is incident angle and 46.7 is reflected angle. Those two are the same, and that's the rule with reflection, that the incident and reflected angle are exactly the same. Okay, now on the other hand, you're looking at this one in red here. This third angle that we're talking about is the angle of refraction. Okay, so look, everybody's familiar with the idea that you stare into the surface of calm water and you can see a certain amount of reflection. You don't see a perfect image of yourself because it's a faded image, but some of the light has been transmitted through the water medium and some has been reflected back. Okay, so there is reflection, certainly, but where's the remaining light go? Well, the remaining light goes into the other medium, which is water in this case, and what happens is it gets refracted, okay? And in a more dense medium, the angle of refraction is less than the angle of incidence, okay? And this is very obvious in this, and if we again compare over to the right, the red angle is 33.2 degrees. That's the refracted angle in the more dense medium, and the incident angle is 46.7. Now, we can vary these, and it simply means that you just move the incident angle and we see an increase in the black. We also see a corresponding increase in the red refracted angle, but the refracted angle red is always less than the incident angle. Okay, and that's for less dense to a more dense medium. And just to mention that, on the right hand side you've got the first index of refraction 1.0003 and the second index of refraction is 1.33. Okay, now I'm just going to confirm that Schnell's law works in this case. And Schnell's law says that the sine of the incident angle divided by the sine of the refracted angle should be equal to the refractive index of the medium that the light is incident on. Okay, so this is 1.33. So I'm just going to test that. So it's going to be sine 64.1 divided by sine 42.6, and we'll just check the answer for that then. Okay, so 64.1, I'm just going to click on that. Okay, 64.1, press the sine, divided by 42.6 sine, and the answer is, yeah, it's 1.3289, which rounded off to 2 decimal places would be this number here, 1.33. So Schnell's law works. The sine of the angle of incidence over the sine of the angle of reflection does indeed give us the refractive index for the second medium, which is 1.33, which it is for water. Okay, and you can see as well then that, you know, if you change the medium, okay, so it is water, but if I change it to glass, you can see how we change the refractive index. We get a 1.46 as the refractive index for the second medium. Our angle of incidence was 64.1, but now you notice that our angle of refraction has changed to 38.1, and this is in accordance with Schnell's law. Okay, so the sine I over sine R, it's got to change because we have a different refractive index. And it's the same then if you test for crown glass, a different type of, you got a 1.52 is your refractive index then for that. So they all have different refractive indices. Okay, I've made a little change now. I have the more dense medium above, so you have the incident light going through the more dense medium and traveling out into a less dense medium. So I've just got to vary the direction of the incident ray. We need to see our refracted ray come back in. Okay, okay, there it is. So we have our incident ray through water and our refracted ray. And you notice that in this case, the black angle is smaller than the red angle, because in the less dense medium, the angle of refraction is greater than the angle of incidence. You also notice well that when we increase the incident angle to a certain point, the actual refraction disappears. The refracted ray continues towards the boundary of the two media, and then it is totally internally reflected. And the angle at which that occurs, it's pretty difficult just to hold it right there. But if you look at the incident angle there, just prior to being totally internally reflected, let me try to stabilize it. That's the best I can do. The angle of incidence is 48.4 degrees. 48.4 degrees, and that's called the critical angle. It's the angle at which the refracted angle is 90 degrees, and beyond that the refracted ray is actually totally internally reflected. It's not 48.4, it's actually a little bigger than that, but it's the best I can do trying to manipulate the incident ray. Okay, so that's that then. Okay, so we've had the idea of interference of two sources of circular waves. Okay, so we've got our black wavefront, another black wavefront, etc., etc., incident passing over through one another. And you see that where you've got the red line, you've got constructive interference. That's black with black. And you've also got a blue line as well, and that's where you have a crest and a trough, and that's destructive interference. That'd be a dark. If this was light you were talking about, the blue would be a dark fringe and the red would be a bright fringe. And you see that you've got several dark and bright fringes to the left and right of the straight blue lines. Okay, so this is the idea we're going to look at now with young slits. Alright, this is perfect. So we've got a double slit scenario, like a diffraction grating, except that we've only got two slits. And in this case, the two slits become then sources of secondary wavelets from the original wavefront. And so what happens then is you get this constructive and destructive interference that I spoke about a minute ago, and on a screen in the background you end up with dark fringes and bright fringes. The straight through ray creates a bright fringe. It's got the highest intensity, and then off to the left and the right you've got your first order fringes. And as we change some of the variables, the wavelengths over on the right hand side here and the spacing between the slits, you'll see that we can change the color of our light for one thing, and we'll also see the effect then of more fringes. Okay, so let's go do that now. Alright, so we're going to vary our wavelength now. I've got it set at 780 nanometers, and that's the red wavelength of light. Okay, visible light. Okay, so we'll just vary the wavelength then, and we see that we changed to 554 nanometers. We're starting to see a second fringe appear, and if I change the wavelength further and make it shorter, you see now that we have both first order and second order fringes. Okay, so I'm going to adjust the wavelength back to the center again, around the 560 nanometers or so. This time I'm going to change the slit distance, and we'll see what effect that has. Okay, so this time you see many fringes starting to appear, many orders of fringes starting to appear. We've got first and second order, now we've got third order coming in, we've got fourth order, and this has all got to do with constructive and destructive interference that's taking place and the effect of the slit spacing and the wavelength, etc. So here's our diffraction grating equation then, and the condition for a maximum or a bright fringe is d sine alpha is equal to k, k lambda. Okay, d is the slit distance, distance between slits I mean to say. Alpha is the angle between the 0th order and either the first, second, or third order, whatever order of fringe you're talking about. K is the particular fringe, whether it be the 0th, the first, second, or third, fourth, whatever, and lambda is the wavelength. That's the condition for maximum. The condition for a minimum is if the waves fronts are half a wavelength out of phase, and that's why we introduce k plus a half. This means a half of a wavelength out of phase, and what that's going to create, a half a wavelength out of phase means that a crest and a trough are going to encounter one another because the difference between crest and a crest is halfway, which would be a trough, and this will give destructive interference and a minimum or a dark fringe.